So my name is Carsten Laxer. I'm currently setting up a new group at EMBL Heidelberg, and to be honest, I was quite surprised when I received the invitation to speak, because I'm not a trained electron crystallographer. So what we do is single particle-based processing with particular emphasis on helical specimen, and we are moving broader into the single particle fields. But I guess the reason why this works in such a workshop is that because a lot of the principles are actually quite the same, and I would hold these kind of talks very similar in a single particle tutorial. While speaking about the fundamentals and the principle, I would like to quickly mention this, and I guess it hasn't been mentioned, that sort of the birthplace or the time of birth for 3D electron microscopy was in the late 1960s at the MRC Laboratory of Molecular Biology in the group surrounding Aaron Klug, where they were able to reconstruct 3D objects from two-dimensional micrographs, and it was with David DeRosier together that they reconstructed a bacterial phage T helical object, and then later on spherical objects with Tony Crowther and Linda Amos. And since then, the field has sort of certain subdisciplines have emerged. One of them are single particle. Each of them are particular, depend on your type of sample you're working with. Then there are icosahedroviruses and helical specimen, and of course, what you all know about 2D crystals. And while there was sort of a discrimination between these disciplines, now it actually appears that we don't really have these strong borderlines. In fact, a lot of the techniques are are merging together. For example, in icosahedral processing, what you now see being published, in particular these high-resolution structures, all of them actually use single particle type of methods. Similarly, also for helical specimens, single particles has been quite successful, and we are already also seeing similar developments in 2D crystallography. So this is the basic outline of my talk. I'm going to spend quite a bit of time talking about the very basics of image processing, things that we deal with every day. I'm trying to explain them in a very sort of fundamental way that you can work out this on test objects where it's easy to understand, and then later on I'm going to spend quite a bit of time on image formation, in particular emphasis on the contrast transfer function in the microscope with some applications. So if you want to understand the properties of an image, it is quite useful to derive a synthetic test image that you understand really well. And one way of doing this is that you design a one-dimensional image that is can be expressed as a series or a superposition of cosine waves. And all of them differ in their frequency, and then you add them all up, and this is what your one-dimensional image looks like. Now, this is what we get in the microscope. And now if we want to understand, you want to characterize this image, for example, according to periodicities, we can calculate the Fourier transform, and we can actually decompose these three cosine functions again. And we can characterize them then, and this will tell us about the content of our image, of course. And there are three major quantities that are being used to describe the Fourier transform. One of them, obviously, is the frequency of your cosine wave, and the second one is the amplitude. And the frequency tells you about the image spacing. Obviously, if you have periodicities in your image, the amplitude tells you how much of a certain frequency component is present. And then there's this third quantity, which is the phase, and that basically tells you where each of these Fourier components is located within the image. Now, if we make this a bit more complex, going to a 2D case, we can construct an image with a two-dimensional sine wave. If you look at the Fourier spectrum, so this is only the amplitudes plotted, you would see discrete frequency. Now we rotate this pattern and have a much higher frequency, so then the spots move further out because we have a reciprocal relationship. Furthermore, we have another sine wave that has a very, very low frequency. It appears very close to the origin. And if we calculate a superposition, we actually can then decompose it into these three sine waves. In the case of 2D crystals, so this is what you would image in the microscope. You have a two-dimensional arrays with defined translation in one plane of molecules, and what you get if you compute the Fourier spectrum, you would see a diffraction pattern which you do not see in this case, but you can be certain. So this is corresponds to several spots. So when we work with images, however, there is one fundamental property we have to take into account, and that is that we are processing these on the computer, and that requires digitization. That also means we need to quantize the data. So if we have any object that we are displaying through an imaging system, we have to put it into an array of numbers. And this is being displayed here. So you have a continuous kind of structure, and then it's being displayed. And we just end up with an array of numbers. And this has important consequences. So one of the consequences is that you have, when you are taking a Fourier transform of discrete functions, you have a maximum resolution by definition, depending on the grid you sampled your function in. And this is, for example, this yellow function is the smallest type of cosine wave that you can use to put on this grid, and this would have a frequency of 2 pixels, basically. So in such a case, we have a real space image. Let's say it's distributed over 20 pixels, which would correspond to 200 angstroms. Therefore, our pixel size is 10 angstroms per pixel, and our maximum resolution that we would ever be able to get is, of course, 20 angstrom resolution, and this is now being plotted here in Fourier space at the very maximum here. 1 over 20 angstrom resolution is the maximum spatial frequency in this case. There is one other important consequence when you think about it. So if you're working with discrete image quantities, so you can also run into a situation that's called aliasing. So basically, it means that if you have a very highly frequent sine wave, and your function is undersampled, so you only can take image quantities at every other frequency, you can actually generate a newer, much lower resolution frequency that is basically an artifact of the system. So all of this works pretty well, in this checkerboard. So let's say your pixels, each of these squares is a multiple of a pixel, 3 or 4 pixels, and you don't have any problems. So you can properly display your object. In the case here, for example, it was chosen in such a way that each of these checkerboard squares has 0.47 pixels, and that, of course, will result in a new frequency, and this kind of overlapping function here is what you see, so an artifact of the system. Another real space kind of illustration for this is if you look at this image here, if you look at these trousers, so they have a sort of a longitudinal pattern in the real space. So this is our original highly accurate image. Then we reduce it. We have to reduce the overall image by 2 times, and then what you end up is actually you get new sort of transverse striation on this pattern, and this is a result of aliasing. And the only way to really get around this is if you apply a low-pass filter before reducing the image, and I guess that can also be a problem when working with highly periodic images. Now let's move on to certain other test objects. So one of them is sort of this binary rectangle, and I find this useful because you can use these type of very simple images and then have them sort of as a repertoire, and to understand your obviously much more complex images. But these are sort of the fundamental rules of it. So here the person has computed a Fourier transform. We don't see anything here, but actually this is not too worrisome because he just used a different convention in displaying this. So if you see here, you see a dot in the upper corners, and this is sometimes what image processing software does. So because we only need half of the of the image to display, we can also start with the origin at the top. However, we are more used to, and you guys also, more looking to diffraction patterns, so you would display the origin at the center of your image. This is what it looks like. It just looks like a strong intensity in the center. Doesn't really tell us much. But if we adjust the intensities according to a log scale, we can actually boost the higher resolution terms, and then you get quite a series of striation, which would then be able to form this kind of sharp edge on the rectangle. So another fundamental principle is that if you rotate now this kind of rectangle by 45 degrees, you actually have the same effect on your Fourier transform. You've rotated now your Fourier transform by 45 degrees. In this case, we rotate by 90 degrees and apply an additional translational shift to the rectangle. And this shows you that it's only sensitive to the rotation, however, translation is not affected by this. This is another property of this. Now we're moving on to another situation like this kind of squared binary rectangle. And we are trying to now understand how you can actually illustrate such a rectangle with the help of these different cosine functions. So one way of doing this is then to kind of mask out in Fourier space. You compute a Fourier transform, and then you mask out all the higher frequencies. What you end up is actually with a rather cosine looking rectangle. And then if you add in more and more higher frequencies, you get much closer to this sharp edge, although you don't see it. And one important take-home message from this slide is that you actually start to see these kind of ripple effects. And these ripple effects are, in the end, high-resolution artifacts that you introduce. And this can be also a problem, dealing with images that you introduce a new periodicity that actually wasn't there at the beginning. And usually the way to get around this in your proper processing is to apply smooth fall of ramps to this. You don't work with hard edges, but you apply a smooth ramp to your rectangle, and then you don't see any of these artifacts. And I think this can be all easily understood if you think about now these, the whole bunch of different cosine functions that will actually make this kind of rectangle. If you exclude the higher resolution ones, you will actually not be able to describe such a hard edge very accurately. So far, I spoke mostly, and this is what most people speak about usually, is amplitudes. However, there is another component that I mentioned. It's the phases. The phases are actually really important. The only problem with that is that the phases are not very intuitive if you display them. In the Fourier spectrum, you can visually interpret this, and this is not the case for the phases. So, however, it is so important, it actually makes a huge difference. So, for example, in this image, if you compute the Fourier spectrum and then just scramble up your phase information randomly or delete it, whatever, you're not going to get anything, and then recompute the Fourier transform. You're not going to get anything close to your image. However, one thing that is, you may have seen this before, so that's more illustrated. If you have two entirely different images and then combine the amplitude component and the phase component, what you actually see in the image is much more like the image that originates where you have the phases from. And this is because it doesn't matter so much how much of your particular frequency component is there, but it matters much more where this particular location is in the image, and that will actually make up your image. So now we are getting into manipulating images. So one of the fundamentals is in image processing is to apply low-pass filters. I spoke about this before. Now it's on a real space image. And there you can grasp that if you cut off all the high frequencies, you can easily discern the overall shape, but of course all the details, the eyes are lost. And the sort of inverse case where you just mask out the low frequencies, there what you get is very high detail, but not very good overall description of this. And then you can think of other situations where you combine these two effects into a bandpass filter. You just have rings of information in Fourier space, and then you get pretty weird-looking structures. But this is all actually not all that unusual, as you will see later on for the M case. So now I told you about a case where we basically just mask out entirely a certain fraction. And this can be described also as a mathematical function. So this is a top hat filter which has a quantity of 1 at these low frequencies and then quantity of 0 at these higher frequencies. However, you can of course also make up other cases where you have now a continuous filter function as for example, Gaussian, and then this way you can actually you avoid a lot of the artifacts that you would introduce in these top hat kind of filters. And then of course you can also design your own type of filter with certain maxima at certain frequencies and so forth. Now this is basically, these are all filters that are basically symmetric, if you will, over Fourier space. However, there are other ones that are not so straightforward to express in mathematical equation, and this is what you would also do in 2D crystallography. So this is one image that was plotted in the newspaper, and you see like you can still see kind of a pattern from the plotter that is there. And if you take a Fourier transform of that image, what you see is you get a continuous transform of the car wheel in the background. However, you do get spots originating from this plotter pattern. So what you can do is you can apply a reject filter, and this is also not very well displayed. So you can actually mask out these certain spots, and what you get out of this is actually the car pretty much with the pattern removed. And the way you do this more practically with the computer, so you compute the Fourier transform of this particular image. You apply your filter function, and that can be anything from a Gaussian to this kind of local filter. And then you back transform it, and you get your image back. And this is a very fundamental operation that people do all the time.
So it's interesting here that you have a logarithm and the exponential function before you calculate the frequency.
No, this is just input and X output, I think. So it's.
You sure?
I think so, yeah.
Not exponential?
I don't think so, no. But I can have a look at it again, but I'm fairly certain, yeah. So now the next, which is related to this kind of filter operation, is the basic idea of convolution. A convolution you can think of in two ways, basically. One of them is the real space way, and this is pretty intuitive. So this is pretty much a 2D crystal situation. You basically have a molecule of interest, and then you have a real space grid. So you want to place that molecule on a very regular binary grid, and then you can go ahead, of course, and apply the translation, and then you end up with a crystal. And this is what you would pretty much do with a convolution. However, the much more straightforward way and more elegant way is to do this in Fourier space, and this is stated in this convolution theorem, is that the convolution of two functions, f and g, is equivalent to the multiplications of their Fourier transforms. And then once you back transform this, you actually end up with your convoluted real space image. And this is what we have in the case of a 2D crystal, for example. However, it will also become more important later on. We see how the images of the microscope are being modulated by the contrast transfer function of the microscope because of the lens settings. So far, we've only talked about periodicities and so on in the image, and it's obvious, of course, that for crystals you get these spots. Everyone knows this. But there's one, and if you think of a 3D crystal, it's also quite obvious that that you would have a spot pattern expanding in all three dimensions. But this is actually different for the 2D case. In the 2D case, we observe diffraction patterns. However, one should note that in the direction perpendicular to the crystal, we don't have any discrete quantities, but we have continuous lattice lines. And this is basically you never observe this continuous lattice line because you can't observe the 90-degree tilt projected through your two-dimensional crystal. But what you do observe is different tilt angles, and thereby each diffraction pattern you can then synthesize this continuous lattice line eventually to end up then with your three-dimensional structure. But I guess this will be also much further explain how to get there throughout the image processing tutorials. There is one other function that is also correlation function, is also a fundamental function in electron microscopy that we basically use all the time. And again, there are two ways of looking at this. So one of them, which is more intuitive, I guess, is in the real space scenario, where we basically have two images. We want to correlate them, basically see how similar they are. So and this is the big deal. We have an array of numbers, and what we do is we slide them on top of each other, and then we form, at each point of this sliding operation, we form the product of these two and then sum them up. And this is what this definition corresponds to. And this is essentially what is important. The second term here in the denominator will actually bring all your values normalized in between 0 and 1, that if you slide an identical image on top of it, you have a correlation of 1, and this is what this meaning is. But in essence, it's just the sum of the products, and this way you can actually sort out images according to their similarity. And one example here is that you have a certain image that you want to further characterize, and you have a reference, and the reference here in the case is the letter A. And then you slide the letter A on top of each other, and you want to find these spots. And of course, this is a fairly straightforward scenario. And what you end up is basically these positions of the letter A. And then in your correlation map, now you get peaks at each of these positions. You get sometime in between, you get kind of an okay peak at other letters, and in between there is obviously no correlation. But the best correlation with the letter A is there. Another function that I told you that if you correlate an image with itself, you would get at the maximum correlation of 1, of course. However, this can be useful in detecting more or less ordered or periodic images. So in this case, this image looks more or less, it has an hexagonal pattern, but you can see it's distorted and so on. So if you want to characterize that, you can perform an autocorrelation. In this way, you end up with this kind of peak pattern that describes exactly the translations that you need at each of these spots. And now I explained convolution, I explained correlation, and actually they are closely related. The problem is just that they are used in very different contexts. So correlation is mostly used in a case where you're trying to match you have a certain reference and so on. As a convolution is more used if you manipulate images. However, they are related in that the simple basic type of operation is similar. It's just that you invert one array of these numbers in the case of convolution. And of course, if you think about it, so if you have a symmetrical filter, this will end up being the same. But mathematically, they are very closely related, although they are used in different contexts. So now I think we have pretty much all the basics to tackle the more kind of applied side for the electron microscopist. And this mainly deals with the question of image formation and contrast transfer function. So the reason why image formation is important to understand, I think, is this basically. So we are trying to understand. We know the positions of a particular atom in our sample, for example, and we want to understand what is our output here. So the conversion from our molecular density to image intensity. And of course, if we know this, then we can actually go back and induce our structure, and this is what we do in our daily lives, actually. So just as a quick recap from what you heard yesterday, the electron beam interacts with our specimen, is being scattered, then being captured by the objective aperture, and then it goes through a diffraction plane, and then later on we actually record our images here. So at this stage of specimen interaction, there's one fundamental property that it very much depends, of course, on the atomic number of our sample, the main atomic number. And then if you look at the periodic system of the elements, you can see a kind of a correlation with higher atomic number. You have a more or less increasing scattering factor. So however, if you compare this with X-ray, X-ray would have a much steeper slope. And the reason for this is that the electron specimen interaction is different. So in the case of X-ray, the X-ray beam interacts with the electrons only, and therefore people also speak of electron density. In the case of EM, we have the combined potential of the nucleus and the surrounding electrons, and therefore we do not, we are actually prohibited to speak of electron density, but we speak of potential density or EM density in general. So, and the reason why we are struggling to get to see something in our images, that we are actually located on the very end here. If we look at proteins of carbon, nitrogen, and oxygen, and we try to get around this, sometimes using negative stain, and then we get a much higher scattering. Another important factor in this is that all of this is dependent on the voltage that you are using. So with increasing electron voltage, you get actually lower contrast, so you have a lower efficiency in the scattering. So more quantitative descriptions. I know we are usually speaking about the elastically scattered electrons when we are trying to talk about image formation. However, there is other components, and this is sort of a quantitative description for real example where we have a specimen embedded in ice, and if we plot the contribution of these four different scattering events as a function of ice thickness that was measured by energy filtering, we see that pretty much our elastic scattering remains more or less the same. However, we have a significant increase in inelastic scattering, and this is the one that gives rise to the foggy kind of nature that we see. However, and then there's other contribution, the unscattered beam, and the interference of the elastically scattered with the unscattered beam actually forms what we call the phase contrast, and this is the major contributor of our image, and I'm going to explain this in more detail. But before I do this, I would like to just also mention a few historic papers where they kind of started to understand this. Yeah.
What means scattered outside the aperture? Is it multiple scattering, or how do they get there, these electrons? In the previous slide.
So outside the aperture, I guess that just means that these are that are not being captured by the lenses, right? I mean, at very high angles.
What happened to these in the sample? it yet?
We have done quite a lot of simulations on that, and what happens is that you have the elastic field is sort of going as shown there, so many of them at once.
So
and as you see the inelastic goes up, and as it goes up, the integral effect is of course what winds up being outside here. I would say the majority of electrons scattered outside the aperture, big samples, or multiple samples. There is a certain fraction which goes, even if you have a thin sample, which goes beyond the aperture, but this is just very small.
Okay, so if you see correct, you might be able to capture the inelastically scattered ones, but not the scattered outside the aperture because they are multiply scattered and lost for good or something like that, possibly.
But you see, there is one thing with all the elastic scattering. The more forward the scattering is, the more delocalized is the corresponding event. And even if you collect those, it will be a blurred image. So basically, to have a sharp image, it's still even with CS corrected lens, better to have it energy filtered. If you really want to go here.
Yeah, so this was one of the first publication on this, so about the basic birth of the term, the tone rings that we now work with all day. So according to that, to the phase contrast theory, they could actually see at that time that once they focused their beam on the carbon grain would dramatically change. And then if they computed, or in that sense they didn't, they just converted it to these micrographs to optical diffraction patterns, and then they could actually see that the carbon grain gives rise to distinct tone rings that is dependent on the defocus. So as we move stronger into under focus, we see more rings and rings appearing, and this was the very first description of this, I believe. And the tone rings are, a fundamental property. We work with them all the time because they are useful in several senses. One of them is that we can detect astigmatism in the images, and this is sort of a schematic figure of what happens during astigmatism. So if you think of your beam that is being captured with two extremes on one position of the lens and then in a plane perpendicular to it, you see that of course they should all end up in the end in one focal point. However, that's not taken for granted, but that can be actually end up in very slightly offset positions, and therefore what is a point becomes a line. And this is what you see in such an image, that your carbon grain is not really a point, but it's being smeared out into space. And a very easy way to detect this is nowadays if you just compute a diffraction pattern, you see an elliptical shape of these tone rings, and then you can use this directly in a way to correct it, although you can also do it in real space. Another important thing that you deal with is sort of the drift of your sample. So this becomes important for stability because we have to take a certain limited exposure time, and we don't want the sample to move during that time. So however, you can detect in the images if you have a preferred orientation of drifting of your image, of continuous drift in this case. In this case, this pattern would correspond to a jumpy type of drift. So this was sort of roughly, I guess people kind of qualitatively looked at this. And the first time people quantitatively looked at this was in the early 1970s, also in Cambridge with Aaron Klug. So they looked at catalase crystals, uniacidly stained, and then they computed the diffraction pattern and then analyzed the type of amplitudes as a function of the defocus. And what they got was a whole bunch of curves, and one obvious thing, for example, was in focus you have a very minimal type of contrast, And then the further you move away, you get actually a reversal in contrast, and this is here shown here. For certain frequencies beyond a certain point, you actually see a reversal in contrast. And then all these kind of data were then combined into the contrast transfer theory, and then they came up with this equation, which has two main components, and they are described as a function of the scattering angle. And the first, so this equation with the Q, that corresponds to what we call the amplitude contrast. And the amplitude contrast very much depends on the type of specimen you're looking at. So for biological specimen, people have been naming numbers from 7 to 14%, so roughly around 10%. With urinoassay, there's also a high discrepancy in numbers around, but it's somewhere between 15 and 30%. And then if we have a closer look at the definition of the phase shift, so this depends on lambda. Lambda corresponds to the wavelength of the electron, so depending on the acceleration voltage that you're using. Then we have the spherical aberration, that is the fundamental lens aberration, that introduces this kind of phase shift. And then we have in this term the defocus that comes into this. And then combining this, you can now plot sort of a function for a particular, or you can predict this kind of function for a particular defocus. And this is essentially now what we are using all the time, and is especially important for recovering high resolution information, because in this kind of range of resolution, pretty much things remain the same, although the amplitudes are modified. You can still see the rough shape of your image. In order to illustrate this, and this is a movie that I got some while ago from Henning. And this is now sort of a real situation case where we just modify the focus in the microscope. So we're moving from underfocus to overfocus. This is now overfocus situation. And if we just look at a particular frequency, now we see that how this contrast actually reverses ongoing all the time. If you were to put down that, or if you were moving the focus knob continuously, as this was displayed here. So in principle, for imaging, for collecting image data, we always trying to use underfocus because of the very low frequency. We usually have a sort of an overlap, and then we have a contrast reversal for the most of the low frequency, and that makes it more complicated, I think, to deal with it. People just rather take it in underfocus, and that really means that it's really in a higher plane than our focal point, and this becomes then later important if you think about specimen height with respect, and of course sometimes specimens have different heights, like in a tilted tilted grid and so on. There's another type of function that's always being used also in the context of the contrast transfer function, and this is the point spread function. The point spread function basically is the equivalent of the contrast transfer function, but then more expressed in the real space scenario. So here we have, this was a test experiment I took from one of Myron Van Heel's reviews. So what he did, he just placed a single pixel inside an image, and then he applied the contrast transfer function to it. And what you see is you get the pixel now, the single pixel spreads. And at the defocus of, this is 0.6 micron and 1.5 micron, you actually see that one pixel now displaces, this image information is now being displaced all the way up to this image boundary, and this is 256 pixels. So if this were to correspond to, this could correspond to a ribosome kind of extension if you think about it, and then so that means a single type of image is being displaced that much. And now, of course, there are ways of dealing with this. And this is, for example, if you just now use a phase flip the information, then you get fairly reliably back your pixel. But I'm going to explain this a bit more in detail. One constructive way I thought in understanding this a bit more in detail is if we look at the synthetic type of real space image, which is this kind of frequency ramp, where we have kind of spatially distributed all the different frequency, and that helps us to understand this. So this is our synthetic real space image, and then if we follow one of these ramps, so if we here go for black, one of these, and we go all the way, it remains black. Now, however, if we apply the contrast transfer function to it, we see that the black all of a sudden becomes white, becomes black again, becomes white, and this is pretty much what you see. So the moment you're moving into this frequency range, which would correspond to this area, then you have a reverse in contrast, again, a reverse in contrast, and so forth. And then also you have this kind of image, the image information is displaced. In order to recover that, you shouldn't cut that off, obviously. So we now get to a bit more kind of applied type of scenarios, like this was done on DMV. If we just look at the 1D profile and we take these images at different foci, you can see, so this is more or less pretty close to focus. You can see, if you now slice through this projection here, then you see how with increasing the focus this changed. All of a sudden, what used to be a fairly rough edge becomes kind of, you see much higher indentation in this, and also the overall shape significantly changes. And it was clear at that time already that you have to take care of this in order to actually get back to your true object. And one thing of doing that at the time was that you just, of course, divide by the CTF in Fourier space, and then that way you would actually get back, because you can simulate that particular CTF function that has modulated your object, and then you can actually get back to your real image. However, this was only done until the first zero intercept in that case, so for the low resolution terms, this was pretty straightforward. And the problem becomes really, what do you do at the first zero intercepts? But there are also now ways of dealing with this. There's one other property that's often mentioned in the context of the contrast transfer function, and this is the envelope, and that is basically defined by the type of gun you're using. So a lot of these advances that we saw in high-resolution structural determination were actually only possible with the introduction of the field emission guns, and that a large degree of it is that they are much more coherent. So in principle, they are much brighter, so 1,000 times brighter, and this way you can have a much higher coherence of your beam. And this is one example with a regular comparison of that kind of envelope function in comparison with thermodynamic force in the dashed case, and at a roughly 3 angstrom resolution, where we would have basically a dampening of 50% of our amplitude. In the case of field emission guns, it's still up to 90% there. And then the further we move out, the less information transfer we have. And there is another thing that is, however, that can be in a way separate, and some people just put it all together, and that is the description of high resolution detail in your images, and that becomes the B factor. And so it was obvious from early analysis that if you compare the computed diffraction amplitudes with your collected diffraction intensities or amplitudes in that case, that there would be, in the ratio, would be a significant fall off. So, and this was done for different types of specimens, and they lead, the further out in resolution that you go, your diffraction pattern just still looks better. And there are several reasons for this, are pretty much sort of summarized in this, and there are probably other contributing factors as well. But so, of course, this kind of decay of amplitudes can then be described quantitatively, and you want to take care of this if you're looking at collecting image data at that resolution in order to compensate for this. One major contribution is, I guess, the radiation damage that you introduce by depositing the dose on the specimen. And then we talked a bit about detectors. There you also lose resolution. You also have charging or mechanical movement, and this, for example, is a case. In the case of diffraction pattern, you don't have this because they are invariant to translation. And then also molecular flexibility in itself can also be described by such a function. In the case of radiation, damages can be pretty much quantified quite well because you can look at the decay of intensities by depositing more and more dose on a specimen. And there is data that under liquid, on a 2D crystal, where under liquid nitrogen conditions, you have a steeper slope than under liquid helium condition that suggests that there is less radiation damage. So I think in principle what now we can learn from all of this thing together is that the contrast transfer function is a fundamental property, and it is quite useful for oneself to kind of play with this kind of function. And there are lots of different tools out in the community where one can actually understand what is going on. And this is one that I use from the EMAN suite, so it's CDF Fit, a program where you just go in and more specify certain parameters, the ones that I talked about, and then you can see how your function behaves. And one of course, the most important we are dealing with is sort of the defocus and amplitude contrast. Again, here others are important: the acceleration voltage and the spherical aberration constant. And then you can sort of plot your CTF and also do this for different type of defoci, and that is usually the way to complement your data. So if you only collected one image at a particular defocus, of course you run into a problem that at this point you don't have any information. But you can recover that information by collecting complementary images at different defocus where you actually result in an overlap, and in this way you can then come to a more or less complete type of reconstruction with a complete information content. What this looks like in the real scenario, so I worked a bit on TMV, so this is a kind of a low defocus for our case, at least image at 1.5, and here you just, if you compare these two images, this is taken at a much higher defocus. You can already see that there is quite a significant difference in contrast. So if we go into this a bit further now from the applied side, so as I say, I'm more from the single particle type of field, so I'm trying to mention roughly the 2D crystal approach, but I guess you will hear about this much more detail, how to do it hands-on, and then also discuss a few of the other approaches that are out there to recover the high-resolution information, because especially in the single particle case, it's not as clear-cut, and people tend to use different kind of solutions. In the case of 2D crystals, however, it's quite straightforward because you can collect side by side actually the diffraction pattern and the image intensities, and the diffraction pattern does not have the contrast transfer function. So if you just look at the ratio between the two, you end up with a function that has these zero intercepts pretty well defined. And what you then do is you just take the second peak and there you phase flip your information. So you invert that contrast. And then on top of it, you do a signal to noise weighting. So this is relying on this ratio between background and peak. And so in this way, you just include those peaks with a certain weight according to the signal that you can see then. And then, of course, in this way, you essentially derive the CTF, but you can already then take in the phase flipped data. In the case of single particles, this is actually not so straightforward. You have to recover that information by heavy averaging. So what you do is you take your micrograph and then tile it up into you tile it up, and then you compute the power spectrum, and then you add these all up, and then you get the tone rings, and you can then use those to fit this manually or automatically, essentially. And you fit this into these kind of ribbons. Of course, if we speak about this, then there is another complication. I showed you quickly about astigmatism. Astigmatism can be pretty well taken care of during the data collection. Nevertheless, you sometimes still introduce slight astigmatism. And this is an example of a program, CTF Find, that deals with this. And here you just need to define this kind of shape in a way, and the way CTF Find defines it is by having a defocus 1 and defocus 2 and perpendicular directions to each other, and then this kind of angle that describes the position of the ellipse, and then you can this can be then used to simulate that particular CTF. Other programs have different type of definition, so one should be careful in treating them. They cannot be interconverted straightforward, or you have to figure this usually out by yourself. So another problem, of course, is that now we can apply, or we can phase flip that information across the entire micrograph. However, that may not be satisfactory. For example, in the case of tilted micrographs. And there's another program that's called CTF Tilt that people tend to use for determining this kind of defocus gradient across the micrograph. And what the program does, it determines basically a strip of overlapping tiles, and this way, of course, along this direction, the gradient remains the same, and then you can average over those and then perform a local fitting with the starting parameters that you use from CTF Find to do that. And as I heard also, I think 2DX uses this kind of approach. So this is sort of just the CTF correction bit. So I spoke about determination. Now the question, how do you correct your images? I alluded in the 2D crystal case. In the single particle case, there are several solutions around, and I'm trying to kind of show you the basic principles around this. So, phase flipping, of course, would still work. However, you have a modification of your amplitudes. CTF multiplication is trying to do kind of a similar signal-to-noise weighting, because you know that at your zero intercept at that particular frequency, you don't have any information content. Why do you want to include it into your images? You don't need to do that, actually. And then, however, at the later stage, you still perform a type of Wiener filtering, because, of course, now your amplitudes are boosted much more than they should be. But one major problem that remains, I think, also becomes clear if you look at synthetic type of test images. So, for example, if you have an object, whatever in this case, you apply certain defocus to it, it becomes, image information is quite displaced. And then you're trying to restore that information. One solution is to just perform the phase flipping. The phase flipping pretty much reconstitutes your object, restores your object. However, you still have sort of a twin object problem in there. And that is because, you can't, there is information lost because of the zero intercept. And similarly, in the case of CTF multiplication, a similar type of scenario, you still have this image information. And one way that tries to get around this as best as possible is the Wiener filter operation, and that works is very much dependent on the signal-to-noise you're using. So if you think about it, the Wiener filter operation is like this. So you can multiply your images that carry a particular defocus already. So you have sort of your images carry a defocus, a CTF squared on them, and then you divide by the CTF square. However, the problem remains at the intercepts, because you can divide by zero, right? So what you have to do is you have to slightly lift that by a certain constant, and that is signal to noise dependent. And this way, you can then recover that information. And here there are 3 scenarios displayed. So, okay, here this is our reference CTF. Then we have a signal, different signal to noise ratios. So the very low signal to noise, the blue curve, is very much equivalent. Then, if you think about it, very low, this becomes a huge term, and then this becomes more or less equivalent to a CTF multiplication. So you have a lot of information missing. So the cryo-EM regular case signal to noise is sort of set around this 9, although it seems to be rather optimistic. And there you recover certain bits, much more information. But if you have a much better signal to noise, then you actually can recover most of the information except for these very tiny bits. And this is sort of the basic idea of this. All right, so this is pretty much what I wanted to say. That there are more things that can be said, I guess, for single particles, but this is not what you guys are here for. And at the very end, I would just like to come up with kind of the information of a nutshell, because David DeRosier, who was one of the first people who did this 3D reconstruction in general, so he was giving these lectures on Fourier transform theory during the AMPO course, and I just copied one of his slides, which I find a very good type of summary of this. So what you should take home from these kind of spots that you get in Fourier transforms. So the very first thing, obviously, so if you have spots, then you get excited. The spot positions tell you about the unit cell size and shape, and this is probably more what Michael is going to talk about. The spot size tells you about the coherence, so how well defined the lattice is, I guess, and then the intensity relative to the background tells you about the signal to noise, and that's being used during the CTF corrections. The distance to the farthest spot, of course, tells you the resolution. So I didn't mention, but obviously the higher your Fourier transform goes, the more resolution you have in your image, until you're actually limited by your Nyquist frequency. The amplitudes and phases of the spots tell you about the actual structure of the molecules. Then we use the positions of the tone rings to determine the amount of defocus, and also the ellipticity to determine the amount of astigmatism. We can actually exclude images according to drift, according to instabilities, and the direction of this asymmetry will also tell us about this instability direction. And with this, I would like to thank you for your attention.
So, how does beam cells manifest itself? Is it okay to say that tone rings could also be caused by beam cells? Yes, correct? Okay. So if you just align your microscope so that your tone rings are round, you could have accidentally corrected beam cells with an astigmatism setting. And then it's still wrong. The phases are still wrong, right?
Yeah. So your phases is still going to be off in a certain way. And that's what's well. So what you would do is that you CDF correct, that is your estimation. And in crystal case, then you can use either inside regular immersion using information of the resolute structure.
Bono told me many years ago that if you want to go better than 5 angstroms, you have to deal with beam cells. that's where single particle microscopy arrives now, and now they start looking into details. As you presented on the photo. So,
model for the noise in order to define the signal to noise ratio. When you approximate or estimate.
Yeah, I think people have tried to look into this more quantitatively. What it boils down to, I think, is still a pretty kind of subjective measure to put in that constant. I mean, in the end, it depends very much also what type of resolution you're interested in. So if you're interested in really in the high resolution, of course, this constant has to be really low in order to see something. But practically, it boils down, you kind of roughly determine this manually. So, yeah.